What usually Chala does is took everything back home, right? Okay, today we are very happy to have Professor Suib, Steve Suib from the University of Connecticut come here to talk about cobalt zeolite catalyst. I know Professor Suib for about 80 years or so. He was my advisor. And see, it is very bad to introduce somebody younger than you and got a professor. And you are hanging here getting nowhere. Almost nowhere.
That's better.
Okay, the only thing I beat him is my wife is pregnant, his wife hasn't pregnant. I'm 35, he's 35, so well, something like that. He graduated from University of Illinois and got his PhD there in organic chemistry, and went to Argonne for 3 months as a postdoc. Actually, that's what he told me, right? Then went to University of Connecticut, Department of Chemistry for the last 8 years, 9 years. Yeah, close to 9. And he had his tenure track 2 years ago, and somehow he arranged his wife got tenure track in the same department.
I didn't arrange that.
Oh, come on. Okay, now we have, today Steve is going to talk about cobalt zeolites.
Thanks a lot, Lena. It's a real pleasure to be here yesterday and today, and had a real great time. Saw the horse park. It's fascinating to see a baby horse. I don't know exactly what you call it. Couldn't tell if it was male or female. So. What I wanted to talk about today were cobalt zeolite catalysts. And we can turn on a slide projector. Oh, wow, do that. Thanks. Yeah. I'm going to be right out here for the camera. I'll stay over here maybe. I won't move around, dance around too much. There we go. How's that?
Focus it a little bit. What light is okay?
Okay, right. That's good.
Okay.
Is that okay, Brian?
Well, the basic idea that we've been trying to investigate is to take a metal complex, either an inorganic coordination complex or an organometallic complex, and put this inside the pores of the zeolite, trap it inside, and then to do some catalytic chemistry. And first question you might ask is, why do you want to use a zeolite? And some of the answers might be here, that they're ordered materials that have crystalline order, many of them. They have three-dimensional pores that are of molecular dimensions. So we can put molecules, real small molecules, inside these pores and get things to react. I think most people here know about zeolite materials. We can control the acidity of the zeolite by ion exchange and other types of techniques. They're very abundant in lots of different types of zeolites. They're typically used in fluid cracking catalysis. And also there's been a lot of interest recently in using these in oxidation reactions. Why do you want to try to encapsulate things? And the second question you might ask. Well, it's known that you can trap organometallic complexes and anchor these types of materials. Zockler's work at Northwestern has been doing a lot of work in this area. This can be done to try to take homogeneous materials, homogeneous catalysts, and put them onto a support and make a homogenized heterogeneous catalyst. The other reason why you might want to do this is try to make new precursors for bimetallous materials. You can think that you might have a metal in there already and bind another organometallic complex to make a bimetallic system, maybe an alloy type system. And finally, you can potentially get, in an encapsulated complex, new stereochemistries. They're going to potentially have different chemical potentials. You control the chemistry inside these porous molecular sieves. And that can result in different chemical and physical properties that we may want. Well, here's a structure of zeolite A, and this is the structure of zeolite X or Y. And again, these dimensions in this pore, you can perhaps see a porous system right here. The dimension of that pore is about 7.4 angstroms. And this dimension is about 4 angstroms. And what zeolites are aluminosilicates. I did this for you. Just kidding. So, these are aluminum silicates. They either have aluminum, silicon, and oxygen in them. And this type bond might be an aluminum, oxygen, silicon, oxygen, aluminum bond. So the aluminum and silicons are in tetrahedral sites, and the aluminums and silicons are, The aluminums and silicons are bridged by oxygen. So if we go around this six-membered ring, we have an aluminum or silicon, an oxygen, aluminum or silicon, oxygen, silicon. So this is an anionic framework, and cations can be exchanged in and out of these materials. It's one of the nice properties that we can make cation exchange zeolites. Typical formula might be this. It's a very big molecule, so water molecules as well are trapped inside here. I'm pretty much going to talk about this structure today. This large proceeding. Well, what are some of the problems of encapsulating a metal complex in the zeolite? What are some of the potential problems? First of all, there's a lot of water in the zeolite, and that could oxidize the metal. You have to worry about that. The second thing is that if you've got a metal inside a pore and you're going to heat this material during a catalytic reaction, it could come outside. And that you'd like to try to prevent that either. It can move either before you use it or while you use it. One of the big problems in this area is characterization. It's pretty difficult to tell whether a metal's inside a pore or outside a pore or both. And that's an important problem. If you put a large molecule inside this pore and you fill it up, then it's going to be difficult to get a reactant in and out, potentially. So that could be a problem. If you heat the material to fairly high temperatures, 300-400 degrees centigrade, the material can become acidic, and you may or may not want that. So that's another parameter we'd like to try to control. The other thing is, I think we all know zeolites are used as molecular sieves or getters to try to grab oxygen, to separate nitrogen from oxygen. They're real good binding agents, and that may be a disadvantage in certain cases. But what are some of the problems of making small metal particles and trying to trap them inside the zeolite? First of all, there's been a lot of work in this area recently, strong metal support interactions, where a support like titanium can creep up around the platinum and cover over the platinum, decrease the surface area on the platinum. Another problem is that oxidation of the metal, these small metal particles are usually very active. They like to oxidize very readily. That can lead to a decrease in the rate of the turnover frequency rate in the reaction. Small metal particles can have different structures than bulk metal particles or larger particles. That you may or may not want that. And finally, during adsorption, there's always the possibility of the structure changing, restructurization by adsorption of different molecules. I guess we have this in there a couple times. But what are the strategies? How can we try to get around some of these kinds of problems? What most people have done in recent years is try to build the complex stepwise. Try to put in maybe the metal, and then if you want organic ligands in there, then add those ligands and try to build the complex inside. Or if you want two metals, put in one metal and then try to put in a second metal. Some people have tried to incorporate complexes into a zeolite gel and try to grow the zeolite around the metal. It's useful in ZSM5 and platinum in that case, platinum ZSM5 materials. And also, you try to use very small complexes that you know can enter the pores. And the types of reagents you might want to use to treat the materials might be for reducing or oxidizing or neutral type species, such as carbon monoxide or hydrogen, oxygen, or salt type materials. So you can treat these materials, metal complexes, with all these different agents. This is one from one of his publications, Dr. Tao's publications. Some of the early work that we did in this area was with iron carbonyl. We took iron carbonyl and absorbed this into a dehydrated zeolite and heated it up under hydrogen for something like 24 hours. And what we found from transmission electron microscopy was that these particles you can perhaps see here are iron particles, fairly large particles, 175 angstrom particles. And it's pretty big, and usually with thermal methods and all, many times the metal comes to the surface. And what Lehman did was he did quite a bit of work with transient studies in these systems, found some very interesting surface intermediates and this sort of thing. But what we really wanted at that time, and maybe not now, but at least at that time, was to try to make extremely small particles and keep them inside the core of the zeolite. That was our original intention. And this talk is in pursuit of that particular goal, actually. And why you might want to do that is related to this type of slide here. This is, again, part of the introduction. There are electronic and geometric effects in catalysis, and I'll talk a little bit about Fischer-Tropsch, not very much, a little bit about Fischer-Tropsch catalysis, CO hydrogen reactions, which Dr. Tollett studied with us. Metals, typically iron, cobalt, ruthenium, rhodium can be used in Fischer-Tropsch reactions. And what we mean by a geometric effect is that either the size or the shape of these metal particles on the surface could influence a catalytic reaction. And also for an electronic effect, we might distinguish that by looking at the degree of electron transfer from the metal to the support or from the support to the metal. So those two effects are what we're very interested in, how those things affect selectivity and activity in a catalytic reaction. Well, these are some data from the literature, some theoretical studies done by some, I believe they're chemical engineers, Hartog and Van Hardenwald. And what these curves are this y-axis represents the number of specific surface atoms. And what I mean by that is the specific surface atoms are either edge atoms or corner atoms or face atoms in a particular crystal structure, divided by the total number of those atoms as a function of particle size. And if we think about that, we think about a face. If we break up that metal particle into smaller and smaller particles, we're going to get fewer and fewer face atoms. We're going to get more and more edge atoms and more corner atoms as we get a smaller and smaller particle size. And what happens here is the number of, and this is sort of backwards perhaps, this is at very large particle size, this is small particle size. As we look at the number of face atoms, as we get the smaller and smaller particle size, they go down. But the number of edge atoms and the number of corner atoms go up. Well, how's this related to catalysis? Well, if a reaction is occurring on that face, and we get small enough, there is a potential that we won't have enough room for all the reactants to react on that face. So really the turnover frequency ought to go down. Now that runs counter to most of the general chemistry and physical chemistry texts that we read. You decrease the particle size, surface area goes up, catalytic activity and selectivity go up. So this is one of the things we're trying to investigate. Well, if you look in the literature and you make a series of curves like this, and we've taken these from like 4 different papers, and look at the turnover frequencies, the number of molecules of methane produced from carbon monoxide and hydrogen per site per unit time as a function of particle size. And this is usually what's not readily available, the particle size and the turnover frequencies. If you do that and you go back and you looked at lots of different reactions, what you can see is for nickel on alumina, the turnover frequency basically goes down as a function of particle size. Cobalt goes down, ruthenium at 1 atmosphere goes down, ruthenium at 4 atmospheres looks like it maximizes. There's a little bit of disagreement depending on condition. The conditions are somewhat different, but if you do this for a series of reactions, and C.O. Bennett has done a lot of this work, a lot of these graphs together at the University of Connecticut with Michel Schiff from the University of Paris, there's not a lot of great agreement on turnover frequencies versus particle sizes, where the particle sizes have been characterized real carefully. This is some work from Cal Bartholomew's lab in Utah. What he's basically found is that in Fischer-Tropsch reaction with 1 atmosphere at 225 degrees centigrade, that the average carbon number of the product does go down as a function of particle size. Other people have verified this sort of thing as well. It's published in Journal of Catalysis in 1985. So there seems to be a structure sensitivity here in terms of particle size and Fischer-Tropsch activity here for gasoline range hydrocarbons. What we want to do, this is what I'll spend the rest of this seminar on. What we want to do is make highly dispersed metal clusters. When we started this work probably 7 years ago or so, the thought was real small metal particles, real high surface area, great catalytic activity and selectivity. We were going to focus on iron and cobalt because it's pretty easy to look at those two metals with lots of different spectroscopic techniques. And our approach has been to hit it with everything you got rather than focus on any one spectroscopic technique. With the hope that if you have a lot of information, you might get a better picture of what's going on in just one technique. And also we wanted to look for geometric and electronic factors in Fischer-Tropsch reactions. I'll also be talking about some cracking and hydrogenolysis reactions, how those are structure-sensitive reactions. Well, if we look in the literature in the early 80s or so of work that was done with zeolites, Jacobs in Belgium has taken ruthenium hexamine complexes, reduced them to hydrogen to ruthenium metal complexes in the zeolite. Lennox Eiten at Argonne has done work with cobalt, do the very same thing. Shea in Paris has taken hydrogen atoms and reacted them with nickel-2 species to form nickel-1 species to reduce these. If you try to do this with iron, it doesn't seem to work. There seems to be an equilibrium. The hydrogen forms acid sites in the zeolite, the iron keeps getting oxidized. Schmidt in Germany has done some work with sodium vapor to reduce iron-2 into metallic iron. Hydrogen gas can be used. Anderson did this in 1975 to reduce iron, but what's found is not all of the iron gets reduced. Some of the iron gets reduced. And Gates at Delaware was one of the first to show that you could use other metals, cadmium vapor, to reduce cobalt ions to metallic. There are a lot of studies here. Reviews just been published in Keynotes and Catalysis on metal reduction and bimetallic systems at zeolite. These are some of the types of techniques that people have used. Different types of reducing agents. Well, this is a method that we've developed in our lab. It basically involves using a microwave plasma to break down organometallic complexes. What we do is take argon gas and flow it through the system. We'll put a metal carbonyl usually, precursor, in one part of this vacuum line, and put a microwave cavity with our zeolite in this well of this cavity, this vacuum line. We'll absorb the organometallic into the cavity and then turn on the plasma and try to decompose the metal carbonyl complex. Now, the reason we went to this is that there's no solvent involved, and we thought we could control all sorts of things, temperature and other things quite nicely. On the next slide I have a description of what's going on here. If you take the metal carbonyl, it's usually either cobalt or iron carbonyl, dimers, and you may need to heat them a little bit to get them to sublime over onto the zeolite. And then treat this with an argon plasma. These are excited state argon species in the plasma. There are lots of electrons in the plasma. There are lots of interesting species there. What we find is we form very small metal particles in the zeolite and argon and carbon monoxide. I'll give you some data for how we know that this mechanism is, how we believe this mechanism is consistent. Well, here's an example. A picture's worth 1,000 words. Here's this plasma here. Here's the metal carbonyl. So we pull a vacuum through here to get all the gas out. Absorb the metal carbonyl onto the zeolite. You can see it's a white powder inside of here. Then we have this microwave cavity. And we turn this on. Well, when we're doing the reaction, there's usually a cage around here, because you know microwaves are sometimes hazardous to our health. We have to put a metal screen mesh around this. We put a dewar around this, and we also blow liquid nitrogen onto this material to keep it cool. And then we have these cage-on fittings and stopcocks, greaseless lines, so we can bring this into a dry box and load it into a catalytic reactor or into a first spectroscopic cell. But it's really quite simple. Now, when I present this work, especially to oil companies, Exxon, Mobil, places like this, people say, "Gee, just like cooking a chicken. You know, you're frying the thing, you're just heating it up." Oh, I want to make one real important point here. People have done that. Rustin Roy has done this, where he's used a commercial microwave oven of 600 watts and he's melted zeolites. His object was to make sols and gills for ceramic purposes. What we're doing, this was published in Journal of Catalysis in '86, is using 0 to 5 watts. We're controlling that power and keeping it as low as possible. And what we think we're doing is selectively breaking the metal carbon bonds that carbon monoxide leaves. If we use 50 watts, we find that the zeolite melts. You can see aluminum metal in an X-ray powder bed. So, I think one of the keys to use this method for making small metal particles is to use a very low power. If you think you've made a real small metal cluster in a zeolite, and you think it's 5, 10, however many angstroms, the real tough part has just begun. You've got to try to prove that's what you have. And that's not an easy thing to do. And that's why we really chose iron and cobalt. It's easy to look at those with lots of different techniques. These are some of the techniques that we'll talk about. Plasma emission, fluorescence. We can look at the fluorescence. That blue glow was the fluorescence from the plasma. We can look at that, do a fluorescence experiment, and see what's there. And we can find out something about that metal deposition process. I'll talk about ferromagnetic resonance today. Really, all that is electron paramagnetic resonance or electron spin resonance, ESR, EPR, on a ferromagnetic material. And iron and cobalt are both ferromagnets. There's cooperative phenomena between the magnetic moments, between the different metal centers that talk to each other. I mean by ferromagnetic system. I won't show any Mossbauer spectroscopy because you might laugh at it from your experience. Well, it's what the real story is with the iron materials. I should tell you this because this is important to the story. I'm only going to talk about cobalt because we finally were able to make these small iron particles, but they carbide just like large iron particles, so they're not extremely useful in terms of catalysis. I'll also talk about electron microscopy, looking at particle sizes and shapes and bulk analysis that we saw yesterday down in the lab. And we've done a lot of other different techniques, and one of the ones I wanted to talk about was spin echo nuclear magnetic resonance. It's a fairly new technique that we've used to look at solid state materials. I think it's a very promising technique, especially for cobalt. Well, what have we done? In terms of luminescence, we're looking at excitation of a molecule to an excited state and looking at emission back down to a ground state, fluorescence. So this is the fluorescence intensity as a function of wavelength for several different systems. This happens to be for argon. Argon has a band here. And carbon monoxide has a series of bands. Well, what we can do if we put this metal carbonyl into the zeolite is start the plasma, it starts to glow, and we just use a monochromator and a detector to scan this fluorescent spectrum as a function of time. And if we put a wavelength in here for carbon monoxide around 384, we can titrate the amount of carbon monoxide coming off the catalyst. And what's happening here is that all of the carbon monoxide is coming off. None of the metal's coming off, because the atomic metal fluorescence is well known. We don't see any of that. So the metal's staying down there on the zeolite, the carbon monoxide is coming off, stoichiometrically. Well, in this ferromagnetic resonance is the second technique I wanted to talk about. Basically, that can be used to look at oxidation states in the material, to look at whether the material is ferromagnetic or not. And this is a plot of the G value, where the signal occurs, as a function of temperature. And if you look in the literature and go through the theory, basically what you can show is that for very small particles of cobalt, that they should have a G value of 2.18. And the lower the temperature at which you observe this 2.18 value, the smaller the particle. That means we look at this at high temperature, the value is fairly high, it comes down, and it reaches 2.18 right about room temperature. If we had a larger particle of cobalt, it would have a curve that would look something like this. It would reach 2.18 at a higher temperature. Now, no one's really calibrated that scale, but I should tell you, for these plasma-produced particles, this is the lowest temperature that we've observed through the literature anywhere, reaching that 2.18 value of room temperature. As far as I know, no one's been able to do that yet. So that suggests these particles are very small, extremely small. And we'll give some other data to try to show that. One of the things I wanted to show you, some of the work we're doing now. Thank you. This is an EPR spectrum on a ferromagnetic material, ferromagnetic resonance, FMR it's called. And this is just the intensity as a function of the value of the magnetic field in kilo-oersted. And the solid line is experimental, and the x's are theoretical fit to the data. And for a super paramagnetic system, that means an extremely small particle that's single domain. All we mean by that is the magnetic moments in this material are all traveling together during this experiment. And they're all the same. There's one domain. All the magnetic moments are aligned. So I mean by single domain, when the particles are extremely small, those are called super paramagnetic particles. And what we've done is fit this with a Hamiltonian that is indicative of super paramagnetic particles. That's pretty good for room temperature. You know, I'll show you there are problems. I'll show you some of the lower temperature data. This one is at minus 60 degrees centigrade, and this is pretty good. This is due to iron 3+ in the zeolites, an impurity in the zeolite. We've used another Hamiltonian to fit that. And the fit isn't so bad. It's okay. But at the very low temperature, see, the fit isn't very good. People have always had trouble trying to fit these types of curves, even at room temperature, actually. And it could be because they didn't realize that there were these iron impurities in there. They only show up, look at the signals getting even larger. They show up at low temperature a lot more readily. What's happening here is that the magnetic moments that are in this, they're not flipping anymore. They're frozen out at low temperature. So the Hamiltonian that describes the super paramagnetic phenomena is just not working. It's no longer super paramagnetic at low temperature. And the reason for that is the system is there are anisotropies. That means that you have to add other terms in there we haven't added in, like the size of the particles and the shape of the particles. All those things have to be added to the Hamiltonian. And that's very difficult to do. So that's why the agreement here is pretty bad. And it's one of the things we're trying to work on right now. So that's ferromagnetic resonance.
What temperature usually start to the kind of cruising effect? You know what?
In lower temperature, where the fit is not so good. Yeah.
I heard it is minus 60.
This one was minus 60. That one was minus 160. That's basically liquid nitrogen temperature. But where do you start to see those effects? That's a good question. We've only done maybe 20-degree intervals. I don't know for sure, but I believe it's also there at 140. Pardon?
160 is
not very well. Yeah. I think so. Yeah. But it's I have a paper on how we did these fits, and their fits were for nickel, so it's hard to make a comparison between the two.
Mostly it depends on the materials.
It depends on the material, depends on the support, all those kinds of things. So it's hard to make a comparison to other things in the literature. It's difficult. I don't know if the angel of this group has done cobalt with FMR, ferromagnetic resonance. I know other techniques with TEM, other NMR. We haven't been able to find any other data to compare to. It would be nice to make that comparison. All we can compare to is nickel on silicon. That's all I've found in the literature.
You can decrease the lower temperature.
I think that's
more.
right. Yeah, I think that's true. Well, here's some transmission electron microscopy data, some TEM data, and these data were collected at Argonne National Lab, their microscopy center. We don't have such an instrument in Connecticut. But if you look real carefully, use your imagination, you can see lattice fringes of the zeolite down here. And so these materials were microtomed, and you can do electron diffraction. And basically, what we observe is that during the catalytic reactions, I'll show you this in a minute. This is after a catalytic reaction. We start to see some metal particles. And they're on the order of 15 to 20 angstroms in size. So these are now outside the zeolite. If the temperature goes above 160 degrees centigrade, particles come out. So we have to keep the temperature below 160 to use these particles in a catalytic reaction. And here's some energy dispersive X-ray analysis to show you. You can see that there's cobalt in the material and silicon and aluminum, all this sort of thing, as you can in your lab here. Basically, what we've found is that if we use 3 watts in our plasma and cobalt carbonyl and sodium X zeolite, we don't see any particles at the surface. And this instrument had a point-to-point resolution of about lateral resolution of 3 angstroms. This instrument we're using at Argonne. After the catalysis, you see particles on the surface if the temperature goes above 160. You can image the lattice in that first slide. And you can get electron diffraction to look at retention of crystallinity. That's another thing. The microwave does not break down the structure. You can do X-ray powder diffraction and show all the zeolite lines are still there. And this, what we used was JEM 100CX at Argonne. Philips Corporation let us use a CM12 to do some other work. We have a Joel 120, which is a real antique in our lab, which doesn't get down too far. It was one of the first ones that Joel ever made. They tell us. But what about this spin echo NMR experiment? There's been some work by Murty, physicist, I believe, at Grambling. He's collaborated with Rao and other people at Pittsburgh Energy Technology Center to do continuous wave NMR experiments like this technique. But in this case, we're talking about a spin echo experiment. And physicists have developed these techniques, and they refer to this in the literature spin echo NMR. And for the chemists that are here, this is not the normal spin echo NMR that we hear about and read about in the literature. This is not the same thing. This is technically, we would probably call it spin echo ferromagnetic resonance, spin echo FMR. And the reason for that is this experiment's done at 0 external magnetic field. There's no magnet. You're relying on the very strong magnetic field of the cobalt particles to do this experiment. And again, it's primarily been used in the physics literature, and Uday Rao's collaborated with Murty at Grambling to do the first experiment, continuous wave. Spin echo is a little bit more sensitive. You can get a little bit more information perhaps with the spin echo technique. What do? You apply a pulse. This pulse is about 2 microsecond pulse length with a separation of 20 microseconds. And what happens is the magnetization starts out, let's say, in the Z direction. So you apply one pulse, and the magnetization goes down into the XY plane. And you apply another pulse, and it goes back over in the same XY plane, 180 degrees out of phase, and that creates an echo. So put in 2 RF pulses, and you have a separation between them. The frequency here is about 50 hertz with respect to a signal which is 219 megahertz. If you know about NMR, these are extremely broad signals. And you talk to other people, say, gee, you can't do NMR on these types of materials. The signals are so broad. Well, you can do it, and they're broad, and there's a little bit of information there. And that's what I want to try to show you. There is a little bit of information there. It's quite useful. There's a critical particle size to this experiment that if you can see particles greater than 40 angstroms in size at room temperature, and you cannot see particles that are around 5 angstroms particle size at liquid helium temperature. And So in liquid helium, we don't see a signal, and we know they're metallic and small, and we know they're around 5 angstroms or smaller. Why cobalt? Well, cobalt has a 100% abundant spin of 59. That's the reason. That's the good news. You know, iron 57 knows about 2.2% abundant. That's the bad news. It's tough to do this experiment on iron unless you label the material. It also has pretty high relative sensitivity and absorption. So iron 57 again is pretty low, and its sensitivity is also quite low. So it's easiest to do this experiment on cobalt. Well, this slide is fairly weak, but I'll try to show you what's going on here. There's a pulse, there's another pulse, and then there's an echo. Here's this echo labeled as A. And then there's another signal, which is a calibration pulse. It's used just to calibrate the signal. And what we're looking at is the echo amplitude as a function of frequency. Another reason why people don't do these experiments is that this is one data point on an NMR curve. You've got to collect this experiment point by point by point. You build up the curve and look at all frequencies to see what's there. And these are home-built spectrometers. So I believe that's why this has pretty much been the realm of physicists. And we're collaborating with physicists to do this work. But what do we see, and why is it so useful? Cobalt metal in a face-centered cubic structure, not treated, has a signal of 219 megahertz. Hexagonal closest back cobalt, on the other hand, has a signal of 230 megahertz. So potentially we can get the structure of the metal particle in this experiment by measuring the frequency. That's very difficult to get from ferromagnetic resonance, lots of other techniques. But what happens if you put cobalt carbonyl, and run that, you don't get any signal? Dicobalt carbonyl in the zeolite that's been sublimed in there, there isn't any signal observed. If you treat this material in the plasma at 3 watts, you don't see any signal. But remember, in ferromagnetic resonance, the data I showed you right here, there's a signal there for cobalt metal particles. We know they're metal particles. We know they're small. We know they're super paramagnetic. That suggests the particles are on the order of 5 angstroms, because the critical particle size of liquid, these are all done in liquid helium, the critical particle size is 5 angstroms. Very small metal particles, highly dispersed. If you take these particles and heat them to 120 degrees centigrade, you don't see a signal. If you take the cobalt carbonyl and sublime it into the zeolite, don't treat it in the plasma, but heat it to 120, you do see a signal. And what that tells us is just thermally heating the material is a different route than the plasma route. But the plasma has somehow stabilized those small metal particles in the zeolite. We're great to see this. We've been saying this from indirect catalytic experiments for years. But here's a pretty direct measurement to say that there's a big difference between thermal activation and plasma activation. Not just from catalytic data, from spectroscopic experiment as well. You can do some other pretty neat things. You can increase the power to 10 watts, and then you start to see the signal, 219, for a bulk kind of a particle. So it's a fairly large particle at that state. If you treat the material in the plasma 3 watts and heat it to 160 degrees, we said the particles centered from the TEM studies, we saw that the particles came out at that temperature. Again, you see face-centered cubic cobalt being formed. But here's some other neat types of things you can do. You can co-adsorb 2 species, cobalt carbonyl as well as ferrocene, C5H5 taken twice iron, and treat it in the plasma at 3 watts. And in this case, we get hexagonal cobalt. So by co-adsorption, placing an iron complex and a cobalt complex in the zeolite, we can control the structure of the resultant particle. Fast, and it's a great technique to tell you that you control the structure as well. Well, gee, this is a catalytic center. We should talk a little about catalysis. How does all this relate to catalysis? And I think with all the techniques we've hit this with, those metal particles in the plasma are really small, 5 angstroms or so. And one of the first things we did, and this is work in collaboration again with Cal Bartholomew, we looked at hydrogen uptake, hydrogen chemisorption at 94 micromoles per gram, essentially 100% dispersed, extremely small particles. this data had to say. That's the good news. The bad news is this. The turnover frequency is extremely low. It's like 10 times smaller than cobalt on aluminum. Not very active materials. Real small, not very active. Very selective though, 26 weight percent C2 to C4 olefins. That's unusual for a cobalt zeolite catalyst of this type, of real small particles. There seems to be a tail off around C9, which may indicate shape selectivity. We're not exactly sure of that. Fischer-Tropsch, we know a lot more about this than I do, that it's tough to get a product distribution and really understand exactly what's going on. The activation energy is relatively low, 75 kilojoules per mole. Here are the weight percent C2 to C4 olefins in the hydrocarbon product. What you see is very high amounts of C3 olefin. And what's interesting, you look in the literature and look at some iron carbonyl complexes produced in France by Bisset and some very small metal particles. They see very high amounts of propylene as well in these reactions. So I don't quite understand that, but other people have observed this type of thing as well. And here are the total weight percentages of C2 to C4 at various temperatures. Here are the alpha values, the largest hydrocarbon that was observed, and the activation energy for 3 different systems. This is our system. It has a fairly low alpha parameter. We observed C7 to C9 or so, 75. Cobalt on silica light. These are data of Marcel Bouquet over in Germany, reported in the International Congress of Catalysis in '84 in Berlin. He sees up to C14, 130, and cobalt on aluminum. This is Kalbach-Balamu's data. Sees up to C20, 96 activation. Again, this was done in collaboration with Kalbach-Balamu. I ought to say also that these small metal particles were sent to about 3 labs, and they all did the chemosorption and all got the same results. If you're going to come out and say you've got 100% dispersed 5 angstrom particle system, it's good to have somebody else backing up on that. So several labs have done that. Well, what do we see? We see that these small metal particles have a very high olefin selectivity. That's the good news. It seems that CO dissociation is decreased somewhat. The rate of hydrogenation must be depressed because we see a lot of olefins. It seems to be a structure-sensitive reaction. This is consistent with their data as well as the data we have. And there may be a shape-selective effect for these very small particles. What are we doing now? What are the types of reactions we're doing now? Well, we're working with a cyclopropane and hydrogen. And we're using a 10-to-1 ratio. And the reason for this is a great test reaction. That cyclopropane can ring open or isomerize to form propylene, or it can hydrogenate to form propane, or it can crack to form methane and ethane, or in a strongly acidic system like a hydrogen-type zeolite, it can oligomerize or polymerize to form butanes and higher hydrocarbons. What's it going to do on these small metal particle systems? That's a hydrogen to cyclopropane ratio 10-to-1, temperature less than 160 to make sure the particles don't sinter. That's another reason for choosing this reaction. If the particles don't sinter, we can study the real small particles. 1 atmosphere, and we're using a thermal conductivity GC. This work is done with Dr. Tao's advisor, Dr. Bennett at UConn. What do we observe? With the small particles, low loading of cobalt in the microwave plasma, at low temperature we see propylene. We only see ring opening. And we see a fairly low turnover frequency as well. But with a high loading, we start to see methane and ethane. We also see propane as well as propylene. Or if we take the small particles and purposely center them at 160 and grow them in stages, what we see is first ring opening, and then hydrogenation, and then cracking. And in general, the small particles at low temperature catalyze ring opening reactions, and large particle catalyze hydrogenation reactions and ring opening. Hydrogenation and hydrogenolysis reactions. Now, how we can explain that, I think, is the following. You have a very small metal particle, cyclopropane comes down, and it ring opens. It doesn't need any hydrogen to do that, even though there's a 10-to-1 ratio of hydrogen to cyclopropane. The particle just isn't big enough. The faces aren't big enough. We heat this up to 116, grow the particles, and we can use the spectroscopy to show that they're about 10 angstroms still in the pores. We get hydrogenation. For hydrogenation, we only need 2 hydrogens to add to form propane. If we sinter these things and drive them out to the surface of the zeolite, make very large particles, we get methane and ethane, cracking, where you need 4 hydrogen atoms. So you just need more surface area, we believe. It's a geometric type effect, flat surface area to make these particles. In fact, we can turn on and off any one of these reactions with very high selectivity. All we conclude. I think this microwave plasma technique is a unique technique to make extremely small particles. Well, they may not be very active, but we can at least make what we think are very small particles that are very consistent throughout the pores, and then purposely sinter them and then grow particles from these. We do have some evidence of geometric effects from catalytic data as well as the spin echo NMR data. We can control the structure, remember, from face-centered cubic to hexagonal places packed. We've done some work with Mossbauer and Iyer to show that there may be some electronic effects. And we believe these Fischer-Tropsch as well as the cyclopropane reactions are structure sensitive. And we're forming superparamagnetic particles that are less active but a lot more selective than these larger particles. Where are we trying to go? We're really trying to control particle size. We thought, remember one of those experiments was 3 watts and 10 watts. 10 watts, you grow the particle. We thought, well, gee, great. Zoom in on the power, 3 watts, we'll get so many angstroms, and 5 watts, we'll get this, and 10 watts, we'll get this. Well, it doesn't work that way. It seems like it's an on and off type thing. There's like a threshold. At 3 you get small, and 5 you get small, but around 10 or so, the particles start to sinter and aggregate, and they just get right out of the zeolite. They move out of the zeolite. So we don't have a lot of control over that. We're continuing to study these reactions because we can make alloys now. If we put down iron carbonyl and cobalt carbonyl, we've been able to make an iron cobalt alloy with this plasma technique. We can show in the NMR, because it has a special frequency, a specific frequency, that it is an alloy. One of the real key things here to fit these data don't fit too well at low temperatures, the size and shape of the particles. We've got to have some handle of what do they really look like. Maybe they're 5 angstroms, or they're flat like a raft, or what do they really look like? And we've used some of the world's best TEMs, and we just can't see these particles. They're just so small. Maybe they're inside the pores. Or how can we get a handle on what the sizes and shapes of those particles are? And finally, some other types of supports like aluminum phosphates and silicon phosphates and other types of molecular sieves. If we don't use a molecular sieve, we can't get particles this small. So we feel what we have to do is take the organometallic, trap it inside, then break it down with the plasma. It has to get in there first. We use aluminum or silica, we can't get these small particles. So it's a fairly specific kind of a technique. It's a disadvantage of it. This is the most important slide of all. These are the people who did all the work. I just talked about it. That's not exactly true. I did a lot of that TEM work myself, believe it or not. And Zhongchao Zhang was the graduate student that did all the sample preparation and Mossbauer work, which I didn't show today. He did the spin echo NMR technique. He went over to the physicist and he said, look, I'd like to hear what your technique is about. He came back with the data. It's very rare when you have a grad student like that. It's really to his credit that this experiment got done. Work. He's a real good student. And he did all the catalysis work as well. Really, really hard worker. Ted Bowden let us use his electron microscope at Phillips, and Lennox Iton collaborated for several years at Argonne National Labs to do TEM work. I didn't talk about this today. Dr. Bennett was really a lot of the brains behind this. He's the guy that suggested cyclopropane and hydrogen. He's really interested in structure sensitivity, and he's given us a lot of guidance through the years. And we learned how to do ultramicrotoming of samples from Jan Hull and Theo Fleischer of Amoco. And finally, the support of the Department of Energy and the Office of Basic Energy Sciences has funded all this work. I'd like to thank all these people, DOE, and I certainly like to thank you for your attention, for letting me come down. Thanks a lot.
the list of your objective, one was to control the acidity of zeolites. I'll believe that. But how do you measure the acidity? What is the most accepted method for measuring the acidity of zeolites?
Yeah, that's a real good question. That's a real key point that I didn't mention here, and that's extremely important because in the ring opening, as well as in the oligomerization, those reactions are catalyzed by Bronsted acid sites. And I'm talking here like we're only worried about the cobalt sites, and that's what's doing the catalytic activity. The turnover frequencies for the Bronsted sites are extremely high. That's one, and these turnover frequencies are very low. The other thing we do is we use sodium vapor. After we've heated the zeolite and dehydrated it, we do that first. I didn't talk all the details of the synthesis. We dehydrate it first, and that could generate some Bronsted acidity. We then pass sodium vapor over that material to drive the equilibrium of sodium metal plus H plus to form hydrogen gas, which takes off the sodium ions to take off all those sites. And the catalytic activity isn't any different in that case. Jacobs has used that technique to try to kill off acid sites. We want to make sure we can try to kill them off so that we're only dealing with a metal site. But how do you measure and how do you look at it? Well, there are lots of different methods, and that's a project that one of the projects we're working on right now. I'll tell you a little bit about. Sorry to drag out the answer so long, but it's really key to this whole thing. People use titrations. That's an extremely difficult thing. Extremely. And your eye is sometimes an effect and all that. People use infrared, and I believe it's not the most sensitive technique in the world for looking at pyridine, pyridinium, catalysts, and all that. Yeah, ammonia, pyridine absorption. We've done some of that. We've done infrared on these systems and don't see much evidence of acid-type sites. Well, it would be really nice, it seems to me, if you could get a technique that was extremely sensitive, that was sensitive to the equilibrium of acid plus base going to acid-base half. And I think that one of the techniques that's pretty good there is fluorescence. It hasn't been used very often, luminescence. So if you had a base molecule, this is something we're working on right now, if you had a base molecule or a series of base molecules, if you have a zeolite with a sodalite cage and a super cage, different size bases, you could effectively titrate each one of the different acid sites in each of those different units by taking a base and looking at different luminescence properties of the base and the acid-base complex.
It's basically Walling indicator method, parallel to that.
Pardon?
Walling indicator method.
Very
much parallel to that.
And you'd like to compare all those, compare the infrared and all, and that's one of the projects we're working on right now. But I think you need a sensitive technique, and the nice thing about the fluorescence is you don't just have to take a steady state spectrum. What you can also do is do a lifetime experiment. Put in a pulse of light from a laser and look at the decay. And the rate of decay, rate is equal to AE to minus KT. For a single exponential, we're going to get a straight line. If there are two species that are underneath that curve, there's going to be another whole term there, A1, A2, KE, e to the minus KT2. You're going to see a double. You're going to see a line like that. So if you use a combination of the lifetime as well as the steady state curve, you might be able to get a handle on it. It turns out pyridine luminescence. So that's where we're going. I think that's a very fundamental problem in all areas. Ceramics, metal, any of those types of things. We're focusing on luminescence to try to do that because it's extremely sensitive. But there are disadvantages there too. Punching. Sorry to drag all that out.
In your sample preparation, I missed how you generate your plasma, and also how did you decide what frequency microwave you wanted to use? And sometimes it seems like you measured the temperature, and other times you just stated the wattage. And I guess you control temperature by how much liquid nitrogen you mentioned to put on the sample.
I didn't talk about the details at this time. I didn't. These slides, the early part of those slides were done a while back. They were talking about patenting and all this kind of stuff.
Okay.
But that's come and gone. It's a process. It's tough to patent the process for that. I'll tell you, I'll detail. I'll tell you in general, what specifically. What we try to do is we have these two wells of quartz. Microwaves can't get into glass, so it's a quartz tube. We put the metal carbonyl precursor in one well. We pull the vacuum from over here and absorb this onto a dehydrated zeolite. Try to make sure all the water's out of there to kill off the acidity, and we treat it with sodium vapor first. So the metal carbonyl comes over and absorbs into the pores. Lots of people believe that from infrared evidence and all. Maybe there's some on the surface. Maybe there's some inside. Maybe both. It goes down. We then put this cavity around it. It's a quarter-wave Evanson microwave cavity. And that's governed by the FCC, the frequency that you use. You just can't go off and use any frequency. And that's unfortunate. So I think that's a key point, that if you could control that frequency, you might be able to break all sorts of bonds and all sorts of different complexes. I think it just happens that the metal carbonyl bond, the metal carbon bond happens to tune into that frequency when the tower is so low at 3 watts. That's my personal opinion. I don't know though. So that's using microwave radiation. Perhaps you could use radio frequency, and there are other types of plasmas as well. So the frequency is pretty much governed by the type of generator you can purchase. I think it's, I can't remember exactly what it is, 2600 or something like that. So that's what the frequency is controlled by, federal regulations. And you can get permission, I think, and you have to build your own systems. They have to be shielded, and you have to have things around them. But what we're doing is measuring the power, the temperature. We're blowing liquid nitrogen gas on the outside of that tube to try to cool it at the same time. That's one of the key things, so you don't get sintering and aggregation. So that's our key thing. It's not in the literature, and hope to put it in the literature soon, to keep the particle size small. But even if you don't do that and you touch the outside of the tube, take the cavity. You can't put a thermocouple in there. It's like putting a metal in a microwave oven. Right? You can't put a thermocouple in there, unfortunately. So what you got to do is rip the thing apart as fast as possible. We touched it. It's a stupid thing to do, but we did it anyway. And it's pretty much room temperature at 3 watts. Now, at 10 watts, it's starting to get hot. It's under 200 degrees. It's starting to get hot thermally. But another question you can ask is, what's the electronic temperature? Because we're passing argon through it, so it's an argon plasma. Okay. So the argon shows the argon tank. I didn't mention there's argon going through there, and the argon is getting excited to an excited state. There are probably excited state atoms, excited state ions. There's lots of electrons in the microwave plasma, and it could be the electrons that are causing the reduction of this as well. You could try to test that with helium and neon and other gases, because that's not going to change. But collisions of helium are not going to be as important. So I have a gut feeling that the electrons are pretty important. There's a lot more electrons in a microwave plasma than in RF or other types of plasmas. So I hope it gives you some kind of feeling. But the excited state energy, which can be related to an electronic temperature, is undoubtedly 2,000 degrees. So that's pretty high. Thermal temperature is cool. With this, and that's the key to the whole thing, keeping that power low, so you don't sinter and fragment and break everything apart. The microwave oven, that's 600 watts. Orders of magnitude higher. Is that sort of
that resolves my questions.
Okay. The mechanism, we don't know the mechanism. How the mechanism works. That would be interesting.
When you disperse the metal so tiny for the zeolites in your surface, then in addition to, for example, then you put carbon monoxide in there, especially this cobalt metal, you form a complex cobalt on the surface. And pretty much doesn't it cover almost most of the zeolite surface? And then the reaction becomes just some sort of a modified cobalt complex type of reaction. Is anything known about this?
Oh yeah, there's a lot known by that. In fact, Mobile Oil and Rao at the Advanced Technology Center, lots of people have suggested that you can take large particles around the surface, and that's the metal function, and things go on there. And in that particular reaction, as the temperature got even higher, very likely the particles were migrating outside. We just didn't have the spectroscopic evidence to show exactly what was happening at the time. But if you keep the temperature low, we believe the cobalt metal particles are still low, still small, and still inside. And there's some people that you got to have a mechanism. How can that happen? If you've got this and it's in a pore and if it's 5 angstroms, there's still a reasonable amount of room in there. Well, even if it's 10 angstroms, how can you handle that? Well, there's lots of different super cages, and they may not all be filled exactly the same way. The other key thing, which good thing you sparked that, is it's extremely low loading of metal. It's extremely low. Otherwise, you use a larger loading, you'll get aggregation and sintering and migration of the surface. So it's like half to 1 weight % metal. That's the key thing. Which means if you calculate all that out, all the pores are not filled. So what if even one is filled? Well, people are talking now in zeolite catalysis about percolation theory. It's called mathematical theory, where it's sort of like there's 3 doors and 4 doors in this room, 5 doors in this room. Well, if we've got a metal particle that are blocking off any one of 4 of these doors, we still got another door open. We have to think of all the possible permutations and combinations of things getting in and around through a pore system to that metal particle. Okay? Blocking access to those sites, that sort of thing. And I don't know, that seems to be a fairly popular theory these days to talk about metals in molecular sieve materials. And we're not real theoreticians. Most theory we've done in ages is try to simulate these types of curves. I don't know.
Those fission strokes are so complex the way they are, and when you start adding more of a site that creates a new pathways, then it becomes even more and more complex.
That's why we're doing cyclopropane now. There are 3 or 4 products that are easy to see. We've done other things like we try to heat the pores, drive things out, and temperature programmed absorption, and try to just if you've got a cutoff like that, that's one of the key questions. C7 and C9, nobody really believes that. The higher hydrocarbons are there, they're trapped inside, or they don't come out. We've tried to get them out, we've tried to do mass balances and all that sort of thing. There's no really firm conclusions. You're right, it's just a real mess. But we haven't observed any of those. But Bartholomew did these reactions as well. He's seen C20. He knows how to see C20 all the way up to C20, probably further. So somehow it's a different system. And I don't know if things are being retained inside and then cracked further. It's not a practical system, but fundamentally it seems to me these things are important. That you can actually make them. You got to go to extreme measures to make them. You use all these weird things like plasmas, but you can make them, and potentially they could be important in maybe other kinds of applications besides catalysis, magnetic particles. But you're right, it's a real mess. It's one of the reasons we got out of it, for sure. We have no idea what's really going on.
Other questions?
In your experiment, I think the sintering, the particle growth, is also a function of the temperature, right?
Yeah.
And I think it's also a function of the time too. Have you ever
The time at temperature.
And I think that you use some different power of the plasma. And have you ever thought about the time? As the time goes by?
Yeah. That's another key point. What's nice about the plasma is that blue glow. That blue glow can be traced to carbon monoxide. It fluoresces. It's a specific wavelength. And the blue is due to carbon monoxide. When all the carbon monoxide comes off, it's pumped out through the vacuum, it goes back to pink, which is due to argon. So all we really do is try to keep that plasma going long enough to break down all the carbon monoxide. We haven't done any prolonged irradiation in there. We've tried to control rather than the time. The time is supposed to be consistent from run to run to run. But we haven't tried to vary that time and keep it in there for a very long time, because from our perspective, the reaction's over with. when you see this color change, and then you can do infrared to show that all the carbon monoxide's gone. That's a real good point. It's interesting. It'd be nice to do some of those kinds of experiments. There's so many variables to control the synthesis. There's the argon, there's the pressure of the argon, there's the metal carbonyl, there's the loading, there's the zeolite, there's whether you cool the cavity, whether you don't cool the cavity. That's another variable that we can control pretty easily at the time. We try to keep it exactly the same. And, I think in terms of if we want to throw these particles later. See, what we've done is we've made these small metal particles in a plasma, but then we thermally sintered them at higher temperatures to purposely try to grow them. That, we've only done that for maybe 4 hours or so at that temperature. That would be interesting to do that for an extended period of time and see how that affects the sintering. And the plasma, yeah, you could do it. I just don't know exactly what you're going to gain unless it does sinter. My feeling is at 3 watts, it's pretty low power. I think it's selectively tuned into that metal carbon bond.
In the experiment, usually how long will it take to plasma for take place
In the tube? Less than an hour. Probably as soon as maybe 20, 30 minutes. We do some other things as well. We use a vibrator to make sure all the particles are moving around, evenly dispersed as well. So typically 20 or 30 minutes. That's going to depend on the loading and how much support you have in there. You could, with a more efficient cavity and small amount sample, you could do it like that. But we want to make enough samples so we can do all these experiments as well as the catalysis and have the same sample. So we're typically dealing 1.5 to 2 grams. That takes about 20 to 30 minutes. Yeah.
With your catalysis, what size of the particle is, what size we are going to make the reaction of the opening, and what size of the particles start to have a carbonation, and what size is the cranking?
Yeah, that's a good question. The propylene are these 5 angstrom particles, the really small ones. The hydrogenation, propane, occurs around 10. We can get that number 10 from several experiments. With iron, we can get it from Mossbauer. From cobalt and iron, we can get it with this spin echo. This ferromagnetic resonance, kind of steady state kind of experiment. And from TEM, we see 15 to 20 for the methane and ethane large type particles. In that case, they must be on it's just too large to be inside. So you can say, it's not, you're comparing apples to oranges, but you just can't make those really large particles in the zeolite, I don't think. 15, 20 initially. So that's something we've got to keep in mind. Probably those particles for the methane and ethane are on the outside. So that's a good question. And those numbers are very, those are very approximate numbers. Pardon?
Possibly. I mean, somebody with that kind of particle size should be more specifically measured by somebody.
You see, you may be thinking about hydrogen chemabsorption, but it's a fairly average. You get an average particle size, and the problem is you have to worry about a couple things. In zeolites, you have spillover. Spillover was observed way back when, and on top of that, you've got potentially an activated process. In fact, we're doing that with Dr. Bennett's group right now, trying to do some hydrogen chemabsorption, hydrogen TPD, temperature programmed desorption, temperature programmed reduction, to try to get at exactly what you're talking about right now. And it's very difficult because think we've eliminated spillover, but they're certainly it's an activated process. Makes it very complicated. So, yeah, you're right. It would be nice someday if you had an electron microscope. As far as I know, no one's been able to see particles of iron and cobalt that are 10 angstroms or smaller. You know, because they just blend into the matrices, whether it's aluminum, silica, or carbon. Van State has tried, and Bartholomew has tried, and Bell has tried. Lots of people have tried. It's a tough problem. I wish we had an answer to it. And these are all approximations from Hamiltonians and spin-echo NMR experiments. Theory says you shouldn't see a particle 5 angstrom size. Is it 5 or is it 6? Or is it 3 or is it 7? But you can see these things grow sequentially, and all the experiments seem to be kind of self-consistent. So my guess is 5, 10, and 15, but those are not hard numbers. You're right.
Any other questions? Any questions? Professor Suib? By the way, Professor Suib has about $800,000 funding for the next 3 years. He's looking for good graduate students. Anybody interested or postdoc, go ahead, talk with Professor Suib. Okay.
He weaseled that information out of me. I didn't volunteer. He kept asking me how much money. The state of Connecticut.
Do you think you have
No, you have to be graduate.
Make one of those submarines that